In the last video, we looked at increasing and decreasing functions. We had a sketch and we said that this was y was equal to some function of x. We can see in the different intervals the gradient is changing. So if we look at the gradient of a tangent in this first interval, we can see now that that will be positive. Or if you like, dy by dx, the gradient function, gave us a positive value. So we had positive, 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 up to now 0. This was where the gradient, or dy by dx, was equal to 0. In this particular case, we said that this stationary point was called a maximum. The gradient to the left is positive, the gradient to the right is negative. Once we come to the right of this maximum stationary point, we had a decreasing function. So we went from increasing to decreasing. The gradient of a tangent, or dy by dx, was less than 0 for all values of x in this particular interval. We then had another stationary point. This one was said to be a minimum, and then to the right again the function was increasing and we had a positive gradient for all values of x in this interval right here. We can see if we've got now the minimum point, the gradient to the left of the minimum is negative, to the right is positive. In this video we're going to consider the nature of stationary points. We've got a maximum, we've got a minimum, or we have now a third one to consider, which is a point of inflection. So let's quickly look at the three different scenarios. What we're going to have then is the maximum, we're going to have the minimum, and we're going to have the point of inflection. So a quick sketch of each, and we will look at some key features. So first one, we'll have a maximum. Working with a quadratic is nice and straightforward, as we can get some idea of where this is going. For the point of inflection, y is equal to x cubed is a nice example. So as we look at this one right here, this is a maximum. So what we have is a function that is initially increasing, then now is 0, and then decreasing. So we're increasing to the left, we're decreasing to the right. With the minimum, we can say now that we will be decreasing to the left, we will be stationary at the bottom, and then increasing to the right. So dy by dx for all values of x, and let's put this here, dy by dx is going to be now greater than 0. At now the stationary point, dy by dx will be equal to 0, and then now to the other side, dy by dx will be less than 0. So all we see now is a maximum point. The minimum, this is going to be the opposite. Dy by dx, the gradient function, is going to be less than 0, 0, and then greater than 0. Now this is a point of inflection. So if we consider now y is equal to x cubed, we can see now to the right of this stationary point. We can tell this is a stationary point as if I take the derivative dy by dx, that gives me 3x squared. So for stationary points, 3x squared will be equal to 0, so x will be equal to 0. So this point right here is a stationary point. To the left, we've got a positive gradient. To the right, we also have a positive gradient. That is what we call a point of inflection. So the gradient is switching from positive to negative, from negative to positive, but in this case, the sign will remain. So if we took y is equal to minus x cubed, then we'd have a negative gradient, a 0 gradient, and then now another negative gradient. In this video, we're going to look at two different methods to find the nature of stationary points. One is a very sort of hands-on approach where we evaluate the gradient at a point close now to the stationary point, and the other method is to use the second derivative. What I'm going to do is start off now with a quadratic. With a quadratic, we can kind of get some idea of what's going on. If we have now f of x is equal to, and we'll take now minus x squared plus 4. Straight off, I can sketch this up and I know what I'm going to have in terms of whether this will be a maximum or minimum. So I've got a negative quadratic, so the parabola looks something like this. This point we know to be 0, 4. We would say that this is going to be a stationary point, and we would say it's a maximum. We can see to the left now the gradient is positive, to the right, so to the left is positive, to the right is negative. So what we're going to do is take the derivative. F dashed of x will be equal to minus 2x. We're going to now look at this stationary point and determine its nature. So the first thing I'm going to write now is for SP, we can say now f dashed of x will be equal to 0. Therefore now what we have is 0 will be equal to minus 2x. clearly then x is going to be equal to 0, and the corresponding y coordinate can be found by subbing it back in to do f of 0. So we can say now stationary point can be given now to be 0, 4. So let's determine the nature. What we do is take some x coordinate here, which I'm going to call A, and some x coordinate here, which I'm going to call B. We do f dashed of A, and we do f dashed of B. So if this is going to yield a positive quantity, and this one yields a negative quantity, then we've got a maximum. If it's the other way around, we have initially a negative and then a positive, we have a minimum. Later on, we will look at the consequences of the point of inflection and consider some basic examples. Now, what I'm going to do is think about an interval. So if I have now A and B, it really doesn't matter. As long as I've got 1 to the left of 0, 1 to the right of 0, that's going to be fine. When we come on to higher order polynomials, so for example a cubic equation, which could have a maximum of 2 turning points, then what we would have to do is consider now a close interval. And we'll look at a case of that shortly. So let's just choose something. Let's make this really quite easy. So what we'll do, we'll define now f dashed, and we'll take A to be -1, and we will now do f dashed, and then we'll take B, so f dashed of 1. So if I sub this in now, remember, this is what we're doing. This is the gradient function. We're not going back now into the original function. All we want to do is find the gradient now at this point where x is equal to -1 and where x is equal to 1. We know what the case is going to be because we can see it. Remember though, some functions we can't accurately sketch, and we have to rely on evaluating the gradient either side of the stationary point. So let's sub that in. That's going to give me 2, and this one's going to give me -2. That is positive, that is negative. Therefore, we have the scenario positive, 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 0, negative, 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 and that can be now stated to be a max. So it's that straightforward. All I've done is taken -1 and put it in there, which gives me 2. I've taken 1, put it in there, it's given me -2. So that's now determined the nature of that stationary point. We found the stationary point by setting the derivative to 0 and evaluated, and then we found the nature of it. In the same way that you could probably appreciate, if we took x squared -5, we would have a minimum. We would have the gradient function, and then we would have now the simple task of choosing a value either side. Okay, let's move on and look at another example. So what I'm going to do is take a cubic equation. Let's say we've got the f of x. So we'll have the f of x, and we'll have now the f of x is going to be equal to, let's go for x cubed, then we'll have plus 3x squared, and then I'll just have a constant. Let's make that -4. So what we want to do is now find the stationary points on this particular curve and determine the nature. If we've got a polynomial here and we've got x to the n, then we have a maximum of n-1 turning points. So with a cubic we can have a maximum of 2 turning points, with a quartic a maximum of 3, as we've seen with the quadratic a maximum of 1, and with a linear function we have 0 stationary points or turning points. Okay, so let's go ahead, let's find these. So what we're going to do is find now the stationary points and determine their nature. So first thing we need to do is find the gradient function, 3x squared plus 6x. So for SP, what we're going to have now is dy by dx, or f dash of x in this case, will be equal to 0. Therefore what we're going to have, 0 will be equal to, and I'll factor this, 3x, x, we're going to have x plus 2. So if we do that now, let's go ahead and look at those. So x plus 2. So we can see now that the x coordinate is either going to be equal to 0, or we're going to have x equal to -2. We can find the corresponding y coordinate by subbing it back into the function. So if we're asked to find the coordinates of the stationary point, rather than just the x coordinate, we need to sub it back in. So if I sub that back in, what am I going to get? I'm going to get 0, -4. If we sub this back in, that's going to give me -8 plus 12 -4. That's going to give me 0. So this is what we have. So these are our stationary points. Now if I wanted, I could get some idea of what this looks like. But again, this isn't granted. You wouldn't always be expected to know what this looks like. But what we've got now are these stationary points. We've got one here, which is 0, minus 4. And then we're going to have 1, and this is quite interesting because that's going to be now on the x-axis. So essentially this is a repeated route to the cubic. So what we're going to do is just go ahead and sketch this. So here's my cubic equation, and then we'll come round to this point right here, and then we'll go back through. So that is the cubic. So what we have here now is this point right here, and we can see from the sketch that that is going to be a maximum. We can see from the sketch that this is going to be a minimum. But say we didn't know that, or say we had now a 3x to the 5th minus 4x to the 4th plus 2x minus 6. We wouldn't know how to sketch this. So we're not always afforded this luxury. So what I'm going to consider now is the nature of these two stationary points. What I'm going to do is this one right here. Now, in this case, I'm going to be fairly tight with the interval. We clearly don't need to be that tight with this interval, but if we had now some cubic function, let's just go ahead and draw a cubic. Let's say I had some cubic function and it did something like this. It came round and it did that, and this was where x is equal to 1. So we had a stationary point here and x is equal to 2. Now if I wanted to evaluate the gradient and I did f dash of 0 and f dashed of 3, then what it's going to give me, that now we can see that this is going to give me a positive gradient, and also 3 is. So if I was trying to determine the nature of this one, I'd need to be a lot tighter with this interval, because we've got another turning point somewhere jammed between this. So what I would look to do in this particular case is f dashed of 0.9 and then f dashed of 1.1. So that's nice and tight, such that we're not passing another stationary point. This one I would do f dashed of 1.9, and then I'd do f dashed of 2.1. 2.1. There we go, f dashed of 2.1. So just be careful in terms of choosing your interval. So let's do this one. And what I'm going to do, I'm going to just do two different ones here. So what we'll do here, we'll do f dashed, and then I'm going to do minus 2.5, and then I'll do f dashed of 1.5. So all I'm doing is considering a point either side. Now we're going to just plug this into a calculator and find the gradient either side of this stationary point to determine its nature. So let's grab up the calculator and let's put in now minus 2.5. So what I want to do is put this now, I'm doing f dashed of minus 2.5. So it's going through here, it's not going through the function here, we're evaluating the gradient. So if I do that, what I'm going to have, this is now going to be my answer. So minus 2.5. 3 lots of my answer squared, plus now 6 lots of my answer. That gives me 15 over 4. So 15 over 4, which kind of, stacks up with what we expected. We got a positive gradient here. Now what we're going to do is let's put in minus 1.5. We're going to put in minus 1.5. So let's now do negative 1.5, or 3 over 2. And then we'll evaluate f dashed of this quantity. So 3 lots of the answer squared, plus now 6 lots of the answer. And that gives me minus 9 over 4. So we can see now minus 9 over 4, that's going to give us a negative. Therefore, we've got a positive gradient to the left, a negative gradient to the right, so we can say that is a maximum. So nice and logical, nice and straightforward. Now with this one, let's go ahead and do f dashed, and we'll make this interval even tighter. Let's go for negative 0.1, and let's do f dashed of 0.1. So if I do that, I'm just choosing these quantities here. We've got negative 0.1, and we'll sub this in. We're going to have 3 lots of that answer squared, plus now 6 lots of that answer. That's going to give me minus 0.57, so minus 0.57. Then I'm going to do f dashed of 0.1. So that's now to the other side of the stationary point. So we'll have now 3 lots of that answer squared, plus 6 lots of that answer, and that gives me 0.63. So in this particular case, we can see that we've gone from negative to positive, therefore we've got now a min. So you can see that anyway, negative, 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 0, positive, positive, positive. So that's now using that particular approach. So we're evaluating the gradient either side. We don't have to do that, and shortly we'll look now at the second derivative. But that's one way that we could do it. We find the stationary points by setting the gradient to 0. That gives us the x-coordinate. We find the corresponding y-coordinate by evaluating it through the function. We determine the nature of the stationary points. by evaluating a quantity either side of that gradient, bearing in mind now that we have to be quite strict. Okay, let's do another one. Let's take a quartic function. Let's say f of x. We'll take now a quartic function. So with this one, let's have x to the fourth, and we'll take minus 2x cubed, and then we'll just add a constant. Let's go for that. So we're going to find now the number of stationary points. We will find the coordinates of them and determine the nature of them. So with a quartic, we're going to have a maximum of 3 stationary points or turning points, and we can look at them now. So let's look at f dashed of x. 4x cubed minus 6x squared. So we can say for SP, so for stationary points now, we can say f dashed of x will be equal to 0. So 0, and I'll factor this, what we're going to have 2x squared, and then we're going to have now 2x minus 3. So in this particular case, we can see now for this equation we have a repeated root of x, and that's going to be x is equal to 0, and then x is equal to 3 over 2. So let's write this out. X is equal to 3 over 2, and then x will be equal to 0. So that gives me the x coordinate of the stationary points. If we want the y coordinate, we're going to have to sub in right here. So if I do that, let's go for 1.5. We will now take this to the 4th power, so let's take that to the 4th power, and then we'll have now minus 2, and then we'll have our answer, and then we will cube this, and then we'll have plus 2. So that's going to give me now 15 over 6. So what, 5 over 16. So what we got then is 3 over 2, 5 over 16. That now is going to be 1. The other is when x is equal to 0, which makes this quite easy because that's just going to give us 0, 2. So this time we don't have the luxury of sketching. I don't know what this is going to look like. We've got these 2 stationary points, and this is going to give rise to something quite interesting with this one right here. Okay, so let's deal with this one right here. So what we're going to do then is consider that when x is equal to 1.5, the gradient now is going to be 0. So what I'm going to do is f dashed of, we'll do 1.4, and then we'll do f dashed of 1.6. So all I'm looking at now is a quantity either side of this particular stationary point to determine its nature. So what I'm going to do in the calculator is put 1.4. We're going to do f dashed of that quantity. So this is going through the function, the derivatives function just here, not this one. So what we're going to have is 4 lots of the answer cubed. Then we're going to have minus 6 lots of the answer squared. That now gives us a total of minus 98 over 125. So minus 98 over 125. So that's a negative quantity. What we'll now do is the f dashed of 1.6. So evaluating the gradient at the x coordinate of 1.6. 4 answer to the power of 3 minus 6 answer squared. That now gives me 128 over 125, positive quantity. So 128 over 125. So what we've got then is negative, 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 0, positive, 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 positive. Therefore, we can state a minimum. So that gives us a minimum. This is now the point where x is equal to 3 over 2. We've got now this point right here. That's where x is going to be equal to 1.4. We've got this point just here, either side now. X is going to be equal to 1.6. Right, let's look at this one now. What we've got is the following. We've got f dashed now of 0. So if I do f dashed of 0, that gives me 0. So what I'm going to do is try something either side. I'm going to do f dashed of negative 0.1, and I'm going to do f dashed of positive 0.1. So subbing this through now the gradient function, what we're going to have is the following. So we're going to have negative 0.1. If we consider now negative 0.1, we're going to have 4 lots of that answer cubed plus minus 6 lots of the answer squared. And that now gives me negative 8 over 125. So let's write that in. That's negative 8 over 125. If we now do 0.1, let's do that one, 0.1, and then we'll evaluate 0.1. We're going to have now 4, then we're going to have the answer, and that's going to be cubed, minus now 6 lots of the answer squared. And that's going to give me now negative, so let's put this in, negative 7 over 125. So what we have here now is the following. We've got negative, 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 0, negative, negative, negative. So this is going to be a point of inflection. So that's what it's going to do. We're going to have now a negative gradient to the left, and then we're going to have a negative gradient to the right. So it's a point of inflection. Let's go ahead and sketch this one up. So let's see what this is going to look like. Let's just have a look at that. So if I type this in now, let's put that in. We've got now, and I'm just going to, let's just pop that in. Right, okay, don't want that. Right, that should work. So what we've got then is this. This is the function that we've just been looking at. So we can see at 1.5 we've got this minimum point which we found, and then at 0 we've got this point of inflection. So all we've done now is come round. This is negative, negative, 0, negative, negative, negative down to the bottom, and then positive. So we've determined the nature of the roots by simply considering the gradient either side of the turning point. So that gives us now the first method that we could use. So that's evaluating. The second method is to use the second derivative. So let's look at using the second derivative. Now the second derivative is the gradient of the gradient function. So if we have a function of x and we find its derivative f dashed of x is equal to 0, this gives us now a stationary point. If we take the second derivative, f double dashed of x, or d2y by dx squared, and this is going to be less than 0, we have a maximum. So what this is saying now is the gradient is decreasing as now the value of x is increasing. So that's the scenario that we have. So if we now take f double dashed of x and this is greater than 0, we end up now with a minimum. So as now the gradient is increasing, x is increasing, or the other way around. As x increases, the gradient is increasing. So let's see what that means. Let's just think logically what this is saying to us. So if we think about this now, if we have a maximum point now, this is the gradient of the gradient function. So we can see now that the gradient is decreasing, this now, and I'll just draw some tangents on here. The gradient is decreasing as now, let's go that way, as x is increasing. And that's going to give us now the maximum point. Yet if we have the other scenario, and this is when x increases, we have now the gradient is increasing. Just consider this scenario. And this now is when the second derivative, f double dash of x, or d2y by dx squared, gives us a minimum. So we end up now with the gradient now of the gradient going to be bigger than 0. So if we just put this here, the other scenario is when f double dash is equal to 0. So f double dash of x is equal to 0, and we need to now investigate further. Now when we say investigate further, what we're looking for is determine whether this is a point of inflection. Two different ways we can do it. We can revert back now to the original method of testing either side of the stationary point, or we can take the third derivative. If the third derivative is not going to be equal to 0, we have now a point of inflection. That though is quite an abstract concept to get your head around, and many pupils simply now evaluate a point either side of that gradient if the second derivative now is going to be a 0 quantity. I think what we're going to do is look now at exactly what's going on here, and we'll take the cubic function that we had before. So what we're going to do is look at that cubic function. Now if I grab that up, we had x cubed plus 3x squared, and then we had minus 4. So let's just type that in, and I'll just go ahead and do that. Let's do that. Right. Okay. So this now is the cubic function. That's what we had. And that doesn't look too dissimilar to the rough sketch that we had. So this now is f of x. If we look at the gradient function, f dashed of x, or dy by dx, and I'll type this in, this is going to be a quadratic function. So we know if we've got a cubic function, let's just type that in, there we go. This now will give me the quadratic. We can see this now is the stationary point on this particular curve. We can see now to the left of the stationary point, the gradient function is positive. If we then look to the right of the stationary point, we can see that the gradient function is negative. And when we're talking about negative and positive, we're saying now above or below the x-axis. Now, all we're looking at is the gradient right here. And then this will be now the minimum point right here of the gradient function. If we now look at the other stationary point, this was just here. This, remember, the green one is the original function. We can see to the left we have now a negative gradient. This is the quadratic, and then as soon as we're past 0, the gradient function is going to be positive. So this is y is equal to the f of x. This now is y we've got, or we could say this is the f of x. This is f dashed of x. What I'm now going to consider is f double dashed of x. Now this will give us a linear function, and that will give us, so we started off with x cubed plus 3x squared minus 4. The gradient function, if we differentiated it, was 3x squared plus 6x. This is going to be 6x plus 6. Now we can see at this point right here, what we've got now is a minimum point of the gradient function, and we can see that that is going to be positive to the right and negative to the left. This point just here is where d2y by dx squared, or f double dash of x, is equal to 0. So we can see to the right of that point the second derivative is positive, and to the left it's going to be negative. In terms of seeing that, I appreciate it's not 100% intuitive, but this now is the function, which is the green one, its first derivative, which is the blue one, and the second one, which is now the second derivative, which is the orange one. And we consider where this is going to be now greater or equal, or greater than 0, equal to 0, or less than 0, when we're looking now at the nature of the stationary points. So we've got the stationary point just here, and we can see at that point right here, the second derivative is less than 0. And then when we consider this stationary point just here, we can see now that at that point right here, we've got now that the second derivative is going to be greater than 0. So does this help the understanding? I would suggest for some it may, but alternatively, it's often seen as quite a formulaic approach to take the second derivative and work with that. So if we go back and look at our functions, so let's take the functions here. We'll start with this one right here. What we're going to do now is to determine the nature of these roots, the nature of these stationary points by taking the second derivative. So what we can do is f double dashed of x. Taking now f of x and differentiating again, this is going to give me 6x plus 6. That is a linear function. We could, of course, if this was y, if we had y is equal to the original function, which was x cubed plus 3x squared, and then we had minus 4, we would say that dy by dx would be equal to 3x squared plus 6x. Then d2y by dx squared would be 6x plus 6. So this is the different notation. So all I'm going to do now is evaluate f double dashed. So what we're going to do is f double dashed of 0. If I do that, what I'm going to end up with is 0 plus 6, that is 6. This now is going to be greater than 0, therefore we've got a minimum. So if we consider that right there, that's this one. Now if I do f double dash, so we're taking now the second derivative and evaluating when that's minus 2, that's going to give me now minus 6. Therefore that is a max. So what we have is the following. That's the max just there, and we've just done that one, and then we've got now the minimum just here. So this is using the second derivative. If we did it for this one right here, we've got f dashed of x is 4x cubed minus 6x squared. So the second derivative, f double dashed of x, is going to be equal to 12x squared minus 12x. So what we need to do is evaluate these. So if I do f double dashed of now 3 over 2, that's going to give me now 12 lots, and then 3 over 2 squared will give me 9 over 4, and then we're going to have minus 12 lots of 3 over 2. So we can see from here that that is going to give me a value here, if we just think about that, we're subtracting now a smaller quantity, so this is going to give us now the positive quantity, and we can see that that is a minimum. If you want to go ahead and do that, what's that going to give us? That's going to give us 27 minus 18, which is going to be 9, which is going to be greater than 0, therefore a minimum. So if the second derivative now is greater than 0, it got a minimum. If it's less than 0, it got a maximum. Now what happens here? If I do now f double dashed of 0, then I'm going to end up with 0. Okay? We're subbing it in now to the second derivative here. So at this stage, what I could go ahead and do now is take the third derivative if I wanted. Now, if I think about the third derivative here, the third derivative, f triple dashed or d3y by dx cubed, is going to give me now, just taking this here, we're going to have now, this is going to be 20, let's write this down, 24x minus 12. So if we evaluate now f triple dashed of 0, that's going to give me minus 12. If this doesn't equal 0, we've got a point of inflection. So if it doesn't equal 0, so we can say f triple dashed of 0 does not equal 0, therefore point of inflection. Or alternatively, you can revert back to the method we looked at before and consider a point either side of that stationary point. So there we go, that's the nature of stationary points, using now a manual method of evaluating the gradient either side, or looking at using the second derivative. In terms of the understanding of those graphs and looking at how they, the nature of them and how they act, I would say that's beyond the scope of the course, but it's been included for completeness.